In this video, we are going to look at the MO diagrams for heteronuclear diatomic molecules. So what I want to do is give you some kind of guiding principles for putting these together, and then just jump right into an example. So the difference in the two atoms is going to give us some differences in the energies of the atomic orbitals. So when we were dealing with homonuclear diatomics, remember I said things like both of these hydrogen atoms are hydrogen atoms, so their 1s orbitals are at the same energy. We'll find that that is now not the case because we have different atoms. It's not going to change the ordering of our energy diagrams, although I'm going to have to give you some guidance about which diagram to pick. It will change some of our pictures. We are going to go through what those pictures look like at the end of this video. All right, so when you're putting these together, the more electronegative atom has a lower energy atomic orbitals. So you will need to show this in a discernible way in your molecular orbital correlation diagrams. The next question is which diagram to use. So do we use first order or second order? I'm going to give you kind of a general rule, and then I'm going to tell you that there are also some exceptions, of course. So first part of this, if both atoms would use the same diagram in their homonuclear versions, use that diagram. And I will give you an example for this. So, Cn, if I asked you to do anything for Cn, it could be Cn neutral, Cn plus, Cn minus, which I guess we don't technically have any examples for cations and anions, but you will deal with those in the exact same ways that you dealt with cations and anions and Lewis structures, in that you just add or lose an electron. So Cn, carbon and nitrogen both appear in the first half, so they use second order, right? So C2 would use second order, N2 would use second order. So Cn uses second order. So Cn uses the same as C2 or N2. If the atoms have different versions in their homonuclears, you should use the first order diagram. So, for example, NO or NO plus or NO minus uses first order, right? N2 would have used second order, O2 would have used first order. This molecule uses first order. If there are any exceptions, I will tell you that it's an exception, and the example that we're going to do is an exception that, depending on what classes you take after this, it's so commonly known as an exception. They may not tell you, but for now, while we're in Gen Chem, I will let you know that this is the case. So let's do an MO correlation diagram for carbon monoxide. So this is an exception, and the way that I would let you know that this is an exception is I would tell you that it uses the C2 ordering. So I'm not going to come out and tell you that it is using a second order diagram, even though we would have predicted it to use a first order, but I'm going to give you a clue. So you would need to know that C2 is second order, and then appropriately draw a second order MO correlation diagram, but with some differences due to the different atoms. So my 3 columns, I'll have my carbon atomic orbitals, my carbon monoxide molecular orbitals, and my oxygen atomic orbitals. And the big, very first thing that we talked about is that oxygen, which is more electronegative, well, first that carbon and oxygen have different energy atomic orbitals. Oxygen is more electronegative, therefore its atomic orbitals are lower in energy. So if I put, say, my 2s for carbon here, the 2s for oxygen should be at a discernibly lower energy. So if you're writing on paper where you kind of always write uphill a little bit or downhill a little bit, you need to take that into account when you put these at different energies. So it's very obvious when we're grading that you meant to put them at 2 different energies. So they're still close enough to overlap. So I will get a sigma 2s and a sigma star 2s. The sigma 2s still has to be lower in energy than both of the atomic orbitals, and the sigma star still has to be higher in energy than both of the atomic orbitals. Even more important here to put these connecting lines to show what came from what. And that's it for that part. So my p orbitals, what do I have to remember? To do a second order diagram and to put the oxygen atomic orbitals at a lower energy. So I'm actually going to fill those in first so I know I have enough space. So if these are my oxygen 2p's, let's put my carbon 2p's up here. Second order means my set of pi 2p bonding is the lowest, then my sigma 2p. The anti-bonding, the sigma star, or not the sigma star, the pi star set is lowest, and then the sigma star 2p. Put in my connecting lines to show what these contribute to. Okay, so I have everything for my second order diagram. Let's fill in some electrons. So carbon has 4 valence electrons. Oxygen has 6. I have 10 electrons total to put in my molecule. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can calculate a bond order for this. So I have 2, 4, 6, 8 electrons in bonding orbitals. I have 2 in anti-bonding. This gives me a bond order of 3. So I'm expecting a triple bond. And if I draw a Lewis structure for carbon monoxide, it's not our favorite Lewis structure, right? Because it has these formal charges, but everybody gets an octet, which we're shooting for ahead of dealing with formal charges. This looks like it matches up pretty well. I have a triple bond in my Lewis structure. I have a bond order of 3 from my MO correlation diagram. I think it looks great. Not that it isn't bad for them to not match. It just means that one explains something about the molecule that the other doesn't. In this case, we're getting consistent results. So this Lewis structure is a good one, even though it's got those formal charges. Okay, so something that we will need to kind of deal with in order to draw our pictures. So the bonding MOs, the way we describe it, bonding MOs are closer in energy to the oxygen atomic orbitals, but instead of writing oxygen, are closer in energy to the more electronegative atom. The anti-bonding MOs are closer in energy to the less electronegative atom. So we will also, from this information, say things like the bonding MOs look more like the more electronegative atom. So here, the bonding MOs are going to look more like oxygen. The anti-bonding MOs are going to look more like carbon. And I just want to label these energy differences and the closeness in energy that we're talking about. We're talking about the vertical energy scale. So the difference between this 2s, make my highlighter a little smaller so it's easier to deal with, the difference in energy between this 2s and this sigma 2s versus the carbon 2s and the sigma 2s, right? Those arrows have different heights. If we look at the same for, let me use a different color here, for the anti-bonding MOs, right, the distance between this 2s and the sigma star 2s is very small compared to the distance between the oxygen 2s and the sigma star 2s. So more electronegative, closer in energy to bonding, less electronegative, closer in energy to anti-bonding, and this influences our pictures. So a couple of words about pictures of heteronuclear molecular orbitals, then some pictures, and then we're done. Okay. So the reason we're here, because atomic orbitals start out at different energies. They don't contribute equally to each MO. So the MO will have a greater contribution from the atomic orbital it is closer to. And the way we show this greater contribution is by drawing that side of the orbital larger. So greater contribution equals bigger in the picture. Which means that we're now going to have to label our pictures with atoms underneath them to show understanding about which one is contributing more. So let's go through all of these pictures for carbon monoxide. So the sigma 2s, do this for CO. My sigma 2s, if my carbon is here and my oxygen is here, it's a bonding MO. It looks more like oxygen. If I go back to my correlation diagram, the oxygen atomic orbital is closer in energy to this MO. So The s orbital on the oxygen side will draw bigger than the s orbital on the carbon side. It looks weird. They're a little weird to draw, but this is our best way of communicating this information. Sigma star 2s, we should find the opposite, right? It's closer in energy to the carbon atomic orbitals. So it's still going to look like a sigma star 2s, but the contribution from carbon will be much bigger than the contribution from oxygen. All right, those are my sigmas. In the 2s, let's do all of my p orbitals. Now let's get this sigma 2p and sigma star 2p out of the way, because these are a little more awkward to draw. The bonding more so. So carbon, oxygen, bonding closer in energy to oxygen. So my p orbital that contributed on the oxygen side is going to look much bigger than the p orbital that contributed on the carbon side. Actually leaves us with this little weird jog in the middle. And then I'm going to shade this. Like always, how you shade it doesn't matter as long as you shade it in a bonding fashion. And so this is my sigma 2p bonding MO, bigger on the oxygen side because it's closer in energy. Sigma star 2p, still carbon than oxygen, still a node, but now this is closer in energy to carbon, so my p orbital on the carbon side will be bigger than my p orbital on the oxygen side, and then I still need to label it as or shade it so that it's an anti-bonding combination. My pi 2p set, right, one from py's and one from pz's. Those are s's. I guess it's kind of hard to show these as plural. So, bonding closer in energy to oxygen. So the one from the set of py's, right, I had it was like a blobby on top. It needs to be bigger on the oxygen side in both of the lobes, because this was like two p orbitals coming together side by side, and I need to label this with atoms. So carbon is on the left, oxygen on the right. For the pz's, still carbon on the left, oxygen on the right. Now it's like a lobe pointing out toward us, bigger on the oxygen side, and a lobe pointing in the back, bigger on the oxygen side. Shaded to show constructive interference. And then the pi stars, they're a little bit easier to deal with. Pi star 2p's, so have a node, carbon, oxygen. The one from the py's, bigger p orbital on the carbon side, smaller p orbital on the oxygen side. And then the one that came from the pz's, still label carbon, oxygen, and a node, bigger pz on the carbon side, smaller pz on the oxygen side. I do want you to be able to draw these pictures, and you should be able to clearly label it with atoms and clearly show the contributions from each atom in the bonding and anti-bonding combinations.